the Proven Performance session. My name is Ryan Tabra. I am the VP and GM of Intel Xeon and Compute Product. I'll be having my good friend and colleague, Ronak Singhal, join me to go into some details on our new Xeon 6. Last quarter we launched the Xeon 6 brand with our 6700 series processor with E-cores. I fondly like to call it Sierra Forest. And then, today, though, we are here and thrilled to launch the next series within the Intel 6 Xeon brand and family, the 6900 series processors with P-cores, or the artist formerly known as Granite Rapids.
Yeah.
So, as Justin just alluded to, we're positioning these products, these family of products you're going to see today, as fitting the needs of today's and tomorrow's data center with our Xeon 6 series CPU processors and Gaudi 3 AI accelerators. Within the Xeon 6 series processors, our E-core products are optimized to give customers the best performance per watt for high-density compute and scale-out workloads. Our more traditional P-core SKUs deliver the best per-core performance for compute-intensive workloads like AI and HPC. And then, of course, with Gaudi, we're being an option for Gen AI models that are in high demand in today's data center. Our processors, and this is just some of the highlights of our new family of processors, are designed with versatility in mind. This enables our customers to consolidate their existing racks and data centers, filling space with higher performant processors to meet their growing demands, all within a similar power envelope. Let's take a look at some of the series highlights. So many of you were there. Last quarter, we launched Sierra Forest, or our Xeon 6, with E-cores in June of 2024. And I can tell you that we're very delighted by the market reaction and our customer reactions. We beat the program schedule that we committed to our customers, enabling them to get pilots up and running on our processors faster. Those pilots are turning into adoption for workloads outside of what we had originally intended, and it's because data centers are ever evolving. We're seeing spaces like networking and storage growing faster than we thought. And we really think this is because of the proliferation of AI data centers pushing this forward. Feedback from customers has been that the efficiency that these E-cores bring, kind of the out-of-box experience and ease of implementing them, is allowing them to consolidate a significant portion of their existing data centers or their greenfield data centers with better performance at the same or lower power envelope. So let's take a look at some of the early results and some of the feedback. This is allowing our customers to take advantage of this efficiency. Kingsoft, a significant partner of ours in China, is seeing a 60% improvement on price per performance. Partners like NTT Data are seeing a 40% less power consumption, and we're pretty thrilled. Intel is very excited to be part of helping them reach their goal of a net zero data center. And then a study comparing E-cores against previous Intel generations and competition is showing a whopping 87% higher performance of the same 350 watt TDP per socket, showing E-cores are not only providing higher power efficiency, but also delivering higher performance at that same TDP. And this is critical for customers like Meta, right? Meta has been using Sierra Forest or the Xeon 6700E to service their growing storage demands, which are exploding in lockstep with their growth in AI. We are proud of what Xeon with E-cores will continue to do for the data center of the future, and we're just looking forward to getting the impact of the rest of the family hitting the market. But today is not just about Sierra Forest or Xeon 6 with E-cores. This is actually the day for Granite Rapids, or our Xeon with P-core. So this is all about P-cores, and without further ado, let's dive in. Our performance cores are uniquely architected to deliver significant performance leaps in critical growth spaces like AI and HPC and databases, while also delivering lower power consumption so our customers can scale without impacting their power constraints. So as they build out new data centers or existing data centers, they can advance their compute. We enable this all while maintaining the same hardware-based security features that our customers expect from Intel, like confidential computing and trust services to keep data secure. The results are in, and we are delivering performance leadership. Intel Xeon 6 with performance cores delivers up to 5.5x the performance increase in AI inferencing using ResNet 50 workloads compared to an AMD EPYC server. And then up to 2.1x performance increase in HPC using OpenFOAM workload compared to an AMD EPYC server. And of course, there's details and stuff that you guys are all used to on how we're actually measuring this and versus what. But this is something that customers are seeing, and actually they're seeing this in real workloads. A little bit more detail. Across a broad range of workloads, this eye chart is supposed to show you that we're killing it, right? It's across the spectrum versus a previous gen. We've delivered flexibility and are delivering an advantage of like the right technology for all the right challenges that our customers are trying to do with their data center. With our P-Core products, we offer the option of MRDIMMs, and for those workloads, there's way more memory bandwidth for those sensitive workloads like HPC and AI. I didn't mean to go. All right. Some highlights, some personal highlights. If you check out the AI space, LLMs are bandwidth intensive and have a good balance of core memory harmonics that let us use a 96 core part, right? And you can see the results there. We've seen other variety of options around the 120 and 72 core parts that we can go into, but the 96 core is what we are showing up here. And also in the AI space, we're seeing over 3 times the performance per core compared to the previous gen, and a Llama 2 7 billion parameter model, and almost 2.5x in Llama 3 8 billion. In HPC, we're seeing a 2.5x of the performance per core in HPC G, and almost 2.5x in OpenFOAM. P-cores are outperforming in perf per watt as well. So it's not just about E-cores and Sierra Forest. Also, Granite is fantastic for performance per watt. And so with you can see that in certain workloads, P-cores are outperforming perf per watt as well, with over 2x in Llama 2 7 billion parameter and 1.73x in HPCG. And of course, and I've had this conversation with some of you in the room, all of these benchmarks are at 100% utilization, right? And so that's what we've been using in industry, and this is where we focus. But as you all know, customers don't actually ever really deploy or intend to have their servers running at 100% utilization. So this next graph we're about to show you is one of my favorites. It's why we're very excited about the Xeon 6 family of products. So as I ask Ronak to come up on stage, what you're going to see is a perf per watt really matters where our customers actually target for real-world deployments. So as we talk to customers, most of them sit and care about what's the perf and perf per watt at 20%, 50%, and 80%. And you can see that the gains are almost 2x versus a previous generation. And I would argue that if you look at some of the competitive solutions out there, this is where Xeon shines. So with that, I'm going to let Ronak dive into the details of why this happens. Hand this off. Take it away, man.
Thank you, sir. So first of all, it's great to see everybody. I don't take for granted being in person. You know, we had to do this remotely a few years ago. We love being in person for this. Had a chance to talk to some of you last night about all of the fun we're going to talk about today. So like Ryan said, on the what we call the load line here, how do we look at our power and performance at different utilizations? What are some of the things that allow us to get these benefits? Obviously, we have the new core compared to what we had on 4th gen and 5th gen. We've upgraded the core to our Intel 3 process. We'll talk a little bit about that later on. So it's the combination of core and process. And then what are the capabilities and algorithms that we've updated around our power management? So when we talked about 4th gen and 5th gen Xeon, we talked about our optimized power mode and how we gave our customers an option to have this lower power mode that they could opt into if they wished. When we get to this generation, optimized power mode is now our default. We've made improvements to that capability such that it's no longer a choice that customers have to make between best performance and best power. Now we have that embedded as our default. And so the numbers that you see here are with our optimized power mode because that's what customers will see out of the box. Underneath the covers, things like how do we maintain and how do we modulate the uncore frequency are part of that optimized power mode. And so we continue to change or update those algorithms to improve our efficiency and improve our performance, and you see the results here. So it's a combination of upgraded core, upgraded process technology, and upgraded algorithms to really focus on that overall load line. And like Ryan said, when we talk to our customers, we obviously share the performance at the 100% point, but we also see an increasing amount of interest in what is your performance and your power at things like the 50% point. Are you able to show a linear power reduction as your utilization changes? Because most of these customers, even the ones that are the largest ones that you all know, are not running typically at that 100%. They're running at 30%, 40%, 50%. They want to understand how they can over-provision their power by taking advantage of that. And then when they have traffic spikes, what does it look like? So today our focus is really going to be on the left-hand side of this page, which is the 6900 series. So this is going to be up to 128 cores. We'll talk about the platform, up to 12 memory channels. In Q1 next year, we'll release the rest of the family of Granite Rapids. And of course, you guys know I'm going to always refer to it as Granite Rapids usually when I'm talking, more so than probably Xeon 6, but they're equivalent. So in Q1, we'll release the rest of the family that goes into the lower core counts, some of the lower TDPs, and it's also on a platform that is really designed for those use cases with lower memory channels and so forth. But today is really around that 6900P, and that's what we're going to focus on. We've talked in the past on how we construct this family of products, but I want to go into that just as a quick refresh once again, so you understand how we're able to build this large set of products with a couple key foundational building blocks. And hopefully you guys got a chance to look at some of the dies that we have up here at the table. If not, you can do that during the break to really get a sense of what this looks like physically. We have two main silicon building blocks that we're using for this family. We have our compute die, or compute chiplet. This is built on the latest process technology with Intel 3. This is what contains our x86 cores, in this case the P cores, or if it's a Sierra Force, it can be with E cores. It contains our second level cache, our third level cache, and the interconnect between the cores. The other foundational piece that we have is our I/O chiplet. That's built on Intel 7, so we are mixing and matching between chiplets of different process technology. The I/O die on Intel 7 is where you see things like your PCIe and your CXL and your UPI connections. You'll note that the memory controllers and the DDR interface are on the compute die. And we'll talk a little bit more about some of the performance advantages of that in a little bit. So the way we construct these parts is literally just aggregating different numbers of compute dies with the I/O tiles. So for the 6900 series, we'll have 3 of those compute dies to be able to get to our 128 cores. But as you saw in the pictures on the prior slide, we have other versions that'll come out in Q1 that will have fewer numbers of compute dies, really to optimize for the core count that we're targeting. So if you look at the platform capabilities that we have on this new product with Xeon 6, the 6900 series, it's a brand new platform. Like I mentioned, it's going to be 12 channels of memory. The memory, like Ryan indicated, will be both DDR5 support, where we'll support up to 6400 in speed, or MRDIMM support, up to 8800 on MRDIMM. And so we'll talk a little bit about the benefits of MRDIMM and what we're seeing with both memory bandwidth as well as applications in a second. But this will be the first CPU on the market with MRDIMM support. We will have, of course, interconnect for doing socket-to-socket communication, which is our UPI links. We'll also have our PCIe, where we'll support up to 96 lanes of Gen 5, and that will also support CXL 2.0. And we'll go into both of those a little bit deeper on the PCIe side as we talk about the role that the CPU plays in these AI systems with accelerators. And then I get a lot of questions from a lot of you about where is CXL? We've heard a lot of hype about CXL. Is that going to start turning into deployment? So we'll talk a little bit about CXL as well. In addition to having the core count, like up to 128 cores, we've also grown our L3 cache. So for those highest cache sizes that we support, we'll support almost, or I should say not almost, but over 500 megabytes worth of cache. And I'll have a SKU stack later on where we'll go through what are the core counts and cache sizes that we support. All the SKUs that you'll see support the fastest memory speed, both on the DDR5 side and the MRDIMM side. So first, let's talk about MRDIMMs, since we're talking about memory bandwidth. The concept of MRDIMMs is simple. You can see the cartoon on the left, but basically taking advantage of the multiple ranks to drive a higher transfer speed across memory. It uses the same DIMM form factor. We have to do a little additional work, obviously, in the silicon to support that. But it is something that we have worked closely with the memory industry to make sure that this is now becoming a standard at JEDEC, and it is something that the memory suppliers will be out there supporting. And some of you have done articles about what you're seeing out in the ecosystem already around MRDIMMs. The performance on here is showing what is the impact of having that higher transfer speed memory on applications, and really focused at applications that are memory bandwidth sensitive, which is not surprising. In this case, we're really focused on traditional HPC applications, as well as some of the AI applications. So if you were to look at this graph and you take something like the stream benchmark, that's giving you an indication on how much just raw bandwidth are we getting as an improvement. So going from 6400 to 8800, we're getting just over 30% memory bandwidth increase. And then how does that 30% translate across a range of applications, like I said, on both the HPC and the AI side? So we see a really good uplift here, because especially when you're talking about being at core counts like 96 cores, or in this case 128 cores, you want to be able to feed those cores. And as we try to maintain the balance between the compute capability and the bandwidth capability, technologies like MRDIMM will become more and more important to being able to feed all those cores. Now let's talk a little bit about CXL. Like I said, I think we started talking about CXL back in 4th gen. That was the introduction of CXL really into the ecosystem. But I think there's been a lot of questions around what is the uptake of CXL? Was that all hype? Is there reality to it? What we're seeing now is that it's taking some time, obviously, for device vendors to build, validate, qualify their silicon. But we're basically going to start seeing real deployments, and when I say deployments, I mean mass deployments at large scale, of CXL usages. And like we've talked about before, the biggest usage of CXL at this time is really going to be about people that want to put memory behind CXL as a means of either expansion or getting more cost-effective memory. So in this generation on 6th Gen Xeon on Granite Rapids, we support CXL 2.0 and the capabilities that come with that. And the other thing that we support that is unique to us, we believe, is what we call our flat memory mode. So if people are deploying a solution where they're expanding their memory with memory over CXL, typically that shows up to applications as another tier of memory because it's longer latency, lower bandwidth, and you want your applications to be aware of what's in that memory so that it can be optimized properly. The concept behind flat memory mode is, what if I eliminate the need for applications to change? What if applications can work seamlessly as they exist today? And the hardware takes care of making sure that the right data is in the right place in the memory hierarchy between being on the CXL side or being on your directly connected DDR. So here we have an example of exactly that. So let me walk you through this example. Imagine a case where I have, as you can see here, the 2.3 terabytes roughly of DRAM. So that's going to be my baseline. I have another case where I have the same amount of memory, but now I have 2/3 of that connected on my standard DDR, and the other third is connected over CXL. And you'll notice that the portion that's over CXL is not even using DDR5 in this case, it's using DDR4. So CXL gives me flexibility as to what memory type I might be using, depending on the device that I'm using. So if you then look at that lower bar where I have the flat 2LM, 1/3 of my memory is going to reside in that connected DDR, and it's always going to be in that. For the other 2/3 of that memory, we will expose it essentially to the operating system such that it all looks like a flat memory. But the hardware will take care of where is that memory placed, in the CXL region or in the DDR region, dynamically based on the profile of the application. So here's a measured result that we have on Granite Rapids Silicon with a CXL device with this configuration, with DDR5 connected to the CPU, DDR4 behind CXL. This is running an in-memory database application, which obviously their in-memory databases are looking for as much capacity as possible to get as much of a database in there as possible. But you also know that the cost of memory is a huge expense to everybody in terms of their TCO, and they're all looking at how do I reduce their expense on that side. So the result here is that by moving from just a flat memory to this hierarchy of memory using a combination of DDR4 and DDR5, we can do that with minimal performance impact, less than 5% performance impact, but the customers are able to get a lower spend on their memory side by taking advantage of our flat memory mode. So we're pretty excited about this. Our customers are pretty excited about this. And like I said, over the course of the next year, I think you're going to start to see deployments around this. The question is, will you even be able to tell they're deploying that, or will it look invisible to many customers? Okay, the next thing I want to talk about is, I mentioned that the memory controllers are directly located on the compute dies. And so when we have that kind of construction, one of the questions comes up is, what is the best way to get my performance? And like we've offered in the past, we have different modes of how you configure your memory relative to the cores in order to get best performance, which may vary by workload. So if you look at the cartoons here, we have two different ways that we can configure our memory. One that we call our hex mode, the other we call SNC3. SNC, for those who aren't familiar, subNUMA clustering. So I'll start with the subNUMA clustering mode. In the subNUMA clustering, we call it SNC3 because you can define 3 NUMA domains. Essentially, each chiplet being a NUMA domain with the 4 memory channels connected to it. This is typically what we're going to see people deploying for highest performance. What you're going to see almost all, if not all, of the benchmarks that we showed today will be in that SNC3 mode. Because what you're able to do is eliminate the need to go and cross over to the other compute dies to reach their memory. And crossing those compute dies does incur additional latency. But there's some workloads that are harder to optimize for those NUMA cases, and you want to have access to the larger pool of memory. Those are the cases where you would use hex mode. And so we do offer our customers the ability to choose, do they want to run in hex, do they want to run in SNC? But like I said, I expect SNC3 to be the most common mode. And here we have some latency differences. The first one on what's the latency for a cache hit. The second one, what's the latency for accessing DRAM. That shows you the difference between our SNC3 mode and our hex mode. Overall, as we grow the number of cores, on 5th gen and 4th gen, you were talking up to 64 cores total. Here, you're up to 128. So we've grown the number of cores by 2x. But we still maintain our cores in a fully connected mesh. So all cores can talk to all of the last level cache, and they can all talk to each other through this. As you grow that, both logically and then physically with the way we're constructing this across the chiplets, it is harder and harder to maintain those latencies. And that's why you see that in the hex cases, the latencies have grown, right? There's no question about that. But then offering the hex as a way to mitigate that for most of the cases that customers care about, we think is a good way to balance that trade-off. So we offer the best of both worlds. If you want fully connected, you can run in hex mode. If you want really best latency, run in SNC mode. All right, so when we talk about the 6900 series, probably the first and foremost use case is going to be in the cloud. Why are the biggest cloud providers so excited about this generation of product? It really comes down to, first and foremost, what is the thing that they want? When they talk to us, the first thing they want is, I want to see TCO reduction at the right performance level. So show me, can you provide that TCO reduction, and how is your performance improving? On their TCO, the first thing they ask is, how many cores can I get? And then as I'm increasing those cores, what performance level am I going to be at? So we have up to the 128 cores, so up to 2x or more, depending on what their baseline deployment was in prior generations. The performance per core will be higher than what we show against our competition. I'll show you a slide on that in a second, as well as versus our prior gen. And Ryan showed you some of the performance per watt improvements we get, and obviously power is a significant part of their TCO as well. So they're looking for density improvements, they're looking for power improvements, and performance uplift. And so that's the combination that we have here with the 6900 series. So I want to have one of our customers talk for a brief second about why they're excited about this product. So we're going to have Google talk a little bit about what they see in it.
At Google Cloud, we deliver workload-optimized infrastructure that enables our customers to harness the potential of AI-enabled applications, cloud-native workloads, and demanding enterprise workloads. Our customers have various applications and workloads composed of many different services with many different requirements. And across this diverse portfolio, they need to be able to lower the cost of running their business without compromising on performance, reliability, or security. So a one-size-fits-all approach doesn't work. That's why earlier this year, we announced 2 new virtual machine families, C4 and N4, the first from a leading cloud provider, built on 5th generation Intel Xeon processors. Taken together, they provide the performance and flexibility our customers need to handle the majority of their general purpose workloads. C4 excels at demanding tasks that need the highest levels of consistent performance, while N4 offers flexible configurations and price performance advantages for optimizing costs and resource utilization. By using C4 and N4 together as the foundation of their cloud infrastructure, Deutsche Börse saw a 15% performance improvement versus prior generations. And we're even more excited about what's coming next. We're looking forward to working with Intel to deliver future solutions based on the Intel 6th generation Xeon scalable processors to enable the latest performance, efficiency, and security benefits. Through our partnership with Intel, we're excited to provide our customers with the cloud computing capabilities they need to innovate, optimize, and deliver on their business priorities.
So, just to recap what you heard there, Google Cloud has come out recently with instances based on Emerald Rapids, based on 5th gen. And they talked about why they're interested about 6th gen, again, around performance, around capabilities like confidential computing, and then getting into the underlying infrastructure benefits that they get around that TCO. So this is a great example from one of obviously the largest hyperscalers on why they're excited about this. Okay, so based on all that, let's start talking a little bit about performance. And the first thing we're going to talk about, again, is in the context of the cloud, where when you have a public cloud provider, it's really not as much about the socket throughput, and we'll talk about socket throughput obviously in a bit, but more so than socket throughput, it's about what is your performance for small VM sizes, because that's what they're renting out to their customers. And so the comparison that we have here is, how does the 6900 series compare to our competition, a 4th gen AMD EPYC part, a Genoa part, on a 16 vCPU VM across, again, a set of workloads. And here what we are showing is that the benefit of the 6900 series of Granite Rapids can be significant depending on the workload. You'll often hear people quote things like spec-in rate. Spec-in rate's a good benchmark because it's broad, it has a lot of different capabilities, but it's only one benchmark. And here you can see that we show that we're on parity depending on how we compile the workload versus what AMD has. And then from there, going forward to what I'll call real workloads that are actually deployed, whether it's HPC-based workloads or AI workloads, and we'll talk more about other workloads in a second. That's where you see the benefit of what we're building. So let's start with AI, because you can't go anywhere without talking about AI. And we're going to talk about the role of the CPU in AI in a couple of different ways. First, about doing actual computes on the CPU. What if I want to run my AI workload on the CPU? What does that look like? The second we'll talk about is how does it look like in an end-to-end flow with your GPU, especially when you have things like your vector database running on the CPU side. And then third, in an accelerated system with a GPU, how do you select what is the best CPU to pair with that GPU, and what are the capabilities you have, and who are the partners we're working with? So those are the three things we'll cover as we talk about AI. So let's start with compute on the CPU. For compute on the CPU, we have the increased number of cores, we have the higher memory bandwidth, we have the larger cache size that we've all talked about. In the 4th gen, in Sapphire Rapids, we introduced AMX, which is our matrix acceleration unit in every core. And so we continue that forward as we go into this generation. The big change in this generation with that is we add support for one more data type. So previously we had 8-bit integer and bfloat 16. Now we also support 16-bit floating point as well in our AMX engine. This graph here is a comparison versus both our competition as well as the prior gen Xeon across a range of AI workloads. The left-hand side being for small LLM models, the right-hand side being more of the traditional AI workloads we've talked about in the past with you, things like BERT and ResNet and DLRM. So you can see the uptake that we have here is significant, both gen versus over gen, as well as versus our competition. And like I said, this is a combination of the bandwidth increase and the compute capability, the doubling of cores being a significant effect. Here, the comparison you'll note is around 96 cores, because a lot of these frameworks have been optimized around that. So we're showing a 96 core to 96 core, core-to-core comparison versus the competition. Speaking of the competition, I want to briefly touch on what they've said about compute on the CPU relative to us, and make sure that everybody understands where we stand. Back at Computex, AMD published the chart at the top here, comparing their upcoming churn, which they haven't launched yet, comparing that to the 5th gen Xeon, and claiming some big compute increases. Following Computex, I think many of you saw that we responded to what they did by saying, hey, when you do benchmarking for AI, it's really, really critical that you use the right software. And we pointed out, we didn't know what software they used, but we pointed out if you use the latest software that is upstream, that is publicly available for us, you will see significant performance improvements over what they published, up to 5x. And so today, we want to build upon that and show what happens if you now run that on the 6900 series. So building upon what we had on the 5th gen, you can see now across the board with the 6900 series, we would be ahead of what they published on the Turin generation for these workloads. So I think one of the key messages is, and I think all of you know this, but just to reinforce, it is super critical when you're doing your benchmarking in general, but especially in the AI space, not just the hardware, but ensuring you have the right software pieces. And obviously, we're going to talk a lot about software through the rest of this morning. This is a key aspect. How do I make sure that the software I have is optimized? Am I investing in those software optimizations, and what do I get for them? Another thing you'll hear us talk about a lot, not just us, you'll hear everybody talk about, is this notion of RAG. And Saurabh will talk about this a little bit later. And one of the components in an end-to-end flow with RAGs is the vector database. Where am I storing all of the embeddings I have for something like a corpus of pictures? And those embeddings are, what are all the different dimensions of information that I have about that picture? Does it have trees? Does it have people? You can do the same thing, obviously, for speech or any other kind of data. So when we look at the role of the CPU on the AI side, what we do in these vector databases, we believe is largely on the CPU today. And so we have two different comparisons here. The first thing you do is you have to build up that database, which is the indexing phase. So here what we're doing is we're doing a comparison again versus the competition using Granite Rapids. And on top of that, taking advantage of one of our software libraries, our Scalable Vector Search, our SVS library, which takes advantage of capabilities like AMX. And so you see the combination of the hardware that comes with the 6900P plus that software library, the comparison we get versus AMD. And here we have it on two different databases, just to show that, that it's more than just dependent on one data set. So that's the left-hand side. The right-hand side then is, all right, once I've built up that index, I need to be able to search into it. And so what is the comparison on that search, again, versus our competition? And you'll see that our performance increase grows as the number of dimensions grows. The number of dimensions being really how much different kinds of information do I have associated with every entry in my database. So this is another example of the role that the CPU plays on the AI front on this vector database side. And we think it's really important to make sure that you understand that flow. So as we talk about RAGs later today, keep that in mind. And you'll see in one of the pictures where we have that located. All right, so the last part I want to talk about on the AI side is what is the role of the CPU in an AI system with an accelerator, whether it's a GPU or whatever is your favorite accelerator. Today, we believe that the majority of the CPUs in these systems are Xeon-based. And we've seen very good uptake from many of the customers. In some cases, even when deploying an AMD GPU, they're using an Intel CPU as the host. And I think some of you have seen those examples. So what are the capabilities that people are looking for when choosing their host CPU? In some cases, they're choosing it based on, I want it to be the same as the infrastructure I have on the compute side. Okay, that makes it easy. In other cases, they're choosing it based on capabilities. What's my I/O bandwidth? What is my performance of the compute on the CPU side? I don't want my GPU to be bottlenecked by my CPU performance. So I want to have really high performance on some number of cores with my CPU. The memory bandwidth can be critical because you want to be able to feed some of the information from the CPU to the GPU. The memory capacity can be important for certain use cases. The reliability, many of you have seen all the discussion about how these large GPU systems or these large AI accelerated systems, the reliability can be a challenge. So making sure that you have the right capabilities for resiliency and for error detection as part of your CPU is critical.
Yeah.
And then finally, just basics like what are the different form factors that you support? Any of you who have built these systems, putting 4 GPUs in a system can be a beast. What is the flexibility we provide around the form factors that we support? DCMHS, if you're not familiar with that, is a standard in the ecosystem around how we build and how we are able to build components in a modular fashion. So we support that. And I'll talk in a second about what we're doing with NVIDIA down in this regards. So we think that the role of the CPU is important in these systems. We talked about the need for data pre-processing, the need for making sure that you're not bottlenecking the GPU. And so that's why we do see people making very clear conscious choices toward Xeon for this use case. Obviously today, NVIDIA is the leader on the GPU side. There's no question about that. So we're partnering closely with them to make sure that as people are deploying MGX or HGX-based systems, we have a full suite of CPUs that have been qualified together with NVIDIA for those systems. So in the chart here, you can see for a range of different system configurations, we offer a range of different SKUs as part of the Granite Rapids family that are qualified with them. And you'll see that this is really just the beginning of some of the collaboration we're doing with NVIDIA. over the course of the next year, you'll see more from us as we talk about ways that we've optimized some of these SKUs very specifically for this use case. But I think this is a great example of how we're working with the ecosystem to ensure the best overall AI system deployments. So that's on the NVIDIA side. Obviously, we're doing the same kind of thing with our own internal accelerators on the Gaudi 3 side. So we'll have the same kind of systems also qualified and validated for those use cases. And you can see, for instance, we'll have both air-cooled and liquid-cooled systems as part of that. Okay, so let's go talk now, do a quick deep dive running through some of the overall performance data that we have. So first, just looking at a broad set of what I'll call general purpose workloads. The left-hand side being general compute, your standard benchmarks. The middle being traditional database kind of workloads. The right-hand side being different, what we call web services workloads. And again, the comparisons here are versus our competition. What we have are versus both Genoa or Bergamo in some cases, so that sometimes we get questions, hey, you're comparing to a 96-core Genoa, but they have this 128-core Bergamo. So we have comparisons in both cases. And you can see the leadership that we're able to provide across the board with the 6900P. Second category we want to talk about are traditional HPC workloads. So in this case, we're only comparing to Genoa because that's more of the applicable comparison point. But we do have the comparison two different ways on the memory side, both with standard DDR5 and then as well with MRDIMM, really for the people who will want to get the highest bandwidth like we talked about earlier. So again, across a broad set of HPC workloads that you're all familiar with, here is the uplift that we're able to get with Granite Rapids. Then the other thing that I think all of you expect from Intel is that the moment we come out with our product on the hardware side, we have all of the software bits ready. They're available, they're upstreamed, they're available from an ISV, they're available in the open source community, and the same is true this generation. So this was just a reminder to say, hey, if you want something that's out there, it's out there. Whether it's your OS, whether it is your AI library, or everything across the board, this is a place where I think we really do lead the industry in being ready, not just on the hardware side, but also on the software side.
Okay.
All right, last thing I want to talk about in the minutes we have left is security. You heard on the Google video, for instance, the importance of confidential computing going forward. A number of our customers, for instance, believe that the world will eventually get to the point where all compute will be done using confidential compute constructs. You see this even starting in the AI front with CPUs plus GPUs. How do you run them in a confidential manner? As people are uploading more and more sensitive data to train these AI engines, how do you make sure that that data is safe? So in this generation, we'll continue to support SGX like we've had before. TDX we started with 4th and 5th gen. We'll continue to build on that as well in this generation with Granite Rapids. And you've started to see some of the cloud providers offer confidential computing in the cloud, offering SGX capabilities, such as at Azure, or TDX capabilities available to their customers at some of the other CSPs. And then on top of that, we have our Intel Tiber Trust and Security. This allows us to offer an attestation service so that people don't have to go through their CSP for that attestation. That way they have separation between who their cloud provider is and the need for that capability. Overall, if you look at some of the security capabilities that we've added in this generation, the first is how do we continue to harden for what's required on the quantum side. The government has put out some regulations about what they expect by 2030. So we want to make sure our firmware, for instance, is quantum resistant. So having those additions as well. Also increasing the capabilities we have around our memory encryption to now use AES 256, as well as the importance of running crypto computes on your CPU itself and making sure that we continue to optimize those is part of what we focused on. There's the hardening of the platform, so being able to do things like encrypt the data as it leaves the CPU, not just to memory, but also to a PCIe device like a GPU. Having physical protection between sockets as well to guard against physical attacks. And then we just talked about confidential computing and continue to increase the capabilities there in response to what our customers are asking for so that they can make confidential computing more and more ubiquitous to their end customers. So I want to finalize with our favorite slide, the SKUs. So you'll see that for the 6900 series, it's a fairly modest set of SKUs. All the SKUs will offer the fastest memory speed, 6400 on DDR, 8800 on the MCR. We didn't talk today about the embedded accelerators like we talked about in Sapphire and Emerald. They're all still there. IAA, DSA, QAT, DLB. And the number of accelerators is the same across all the SKUs. Where we do vary those SKUs is by core count, by TDP, and as a result of those, obviously the frequency will also vary. The other thing to keep in mind is these are what we call our roadmap SKUs. So these are the SKUs that if you go to Intel.com, you say, hey, what are the Grand Rapids SKUs? This is what you see. On top of this, we have the SKUs that we work with each of our key customers in terms of being able to customize what they want. So you heard Google talk about why they're so excited about Xeon 6. I think many of you probably saw the press release yesterday between Intel and Amazon. And in that press release, they talk about the customized Xeon 6 that we'll be working with directly with Amazon on. So you can think of that as these are the starting points we have for our products, and then we work with them to customize across whatever dimension they want to customize in. So keep that in mind as you think about how does this fit into our portfolio. So this is today. In Q1, we're going to have the next series. So I'll welcome Ryan back to I think you have a little toy there. What is that?
I do. This is Grand Rapids AP or Xeon 6 with P cores. We're very excited to be finally launching this game-changing product. Thank you for being here and listening about all the technical details.